Welcome to the session on air tightness and air sealing. Um, First off with introductions, my name is Sam Myers. I serve as a building science consultant and trainer for RetroTech. So I conduct a lot of studies in the field, answer a lot of your questions, control our social media accounts, go to conferences and present and hold down our trade show booth. That was before COVID-19. So now we're living in the world of Zoom as we are putting everything virtually until things get back to normal. And I'm located in Wilmington, North Carolina, which is on the coast. Before my time at RetroTech, I was with a company called Advanced Energy, where I was a building science specialist with them, spending a lot of time in the field doing building diagnostic testing, blower door duct testing, and helping build some standards for our local program there. And along with us today is Mr. Clint Shireman from Knauf Insulation. Clint is a trainer for Knauf. You've probably seen some of their new videos that have been circulating around to show the do's and don'ts of installing insulation and air sealing. Clint, I will let you do a little bit more of the introduction for you here.
So I'm a trainer. One of the unique things, we only make one type of insulation, and that's fiberglass. But when I was hired on, the entire mission that I was given, which I think is pretty unique, was that it doesn't matter what's being used. We want people to do it right. So I train, of course, with our products, but still answer a lot of questions and help with just general application knowledge and building science with a broad spectrum of things. So I think that's good that, we of course want to sell more fiberglass at the end of the day, but we are also trying to push further the mission of doing it right the first time. Prior to Knauf, I was doing remodels, and that was the world that I lived in, doing whole house remodels. Very little with energy actually, until I came to Knauf. But we did some insulation here and there when it was needed, but not a whole lot. And then just a fun bullet point here, Sam. Last year when we were still having conferences, I won the Habitat X Blower Door Challenge.
Where did your guess come from again?
I think realistically, I was talking to Joe Medosh, and we had similar lines of thought, but he of course knew how to dial numbers in, and then I just guessed close to Joe. So,
well, didn't it come from a Rush album?
It was a Rush album, yeah, because he was like 22 something, and 2200 CFM, and I decided to just be funny, and I would do 2112. So,
and it worked,
and it was like 2123 or something. So I was really close. So.
Yeah, so for those of you who have never heard of the Habitat X event, it's put on by Chris Dorsey, who is one of the authors of the Residential Energy book, which is kind of considered the Bible of the home performance industry. And this is a small conference he puts on every year. Unfortunately, it's another one that didn't happen this year, just like many others. But Clint and I actually met there a couple of years ago, and we've been crossing paths at different events ever since. So we decided this would be a good session for us to team up on. The way that we'll have this broken down, I'm going to talk first about how to do air tightness testing on a house. So it'll be kind of like a quick crash course on air tightness testing and how to use that same equipment to find leaks. Then Clint's going to take over and talk about more about how houses leak and some of the best practices to seal them up. So Clint, thanks for partnering with me on this.
My pleasure.
Sure. So I will go ahead and kick this off with just some introductory air tightness stuff. A little bit about the how a house leaks air, why we care about this kind of thing, and what we do about it. So why do we care about air tightness in homes? Rarely do you ever get a homeowner call with an emergency air leak. It's usually not something a lot of homeowners think about. It's out of sight, out of mind. But we do this either to meet the code or to ensure quality control, whether if it's a builder or an insulator or an HVAC contractor. It's just a good way to keep tabs on that house to make sure it's going to be of the highest quality. And a big thing that's come around here over the past, I'd say, decade, and it's getting more and more popular, especially with home buyers, is indoor air quality. This is a nice little model that our friend Joe Medosh came up with that shows some of the things that can collect inside of a stud bay in an older, leakier home. You can see Larry Zarker from BPI here. Would you want to breathe that in? You kind of look at the stuff that settles in there, and if you think about some of the things that go on inside of the walls of leaky houses, you get pests coming in, you have maybe some rodents coming in, pollen, dust, things like that. And if you think about the air you breathe inside of your home, where does it come from? It comes from somewhere. Well, it comes from outside, but it has to pass through your exterior walls first. And you think about the kind of things that it might pick up in there before it hits your lungs when you take a breath. So air tightness has a whole lot to do with indoor air quality. So that's another reason. It's not just energy, comfort, indoor air quality and durability have a lot to do with it as well, as we spell out here. For those who aren't really savvy on home performance, maybe you're run-of-the-mill homeowner or something like that. When you think about upgrading your house, a lot of people think about the doors and the windows. It seems pretty obvious. There's big holes in the walls, but really, if you look at this chart here, it's actually a smaller sliver of the pie. There's a lot more other areas that we should focus on if we're looking at an existing home and wanting to improve it. As you can see, floors, ceilings, and walls that don't have anything to do with doors and windows take up about a third of that chart. And when you add other penetrations, like whether it's plumbing, electrical, mechanical, fireplaces, and maybe leaks in the ductwork, that's well over half. So this is what we're going to give some examples of today. And I wanted to mention the durability also, because especially where I live in the Southeast, we have really high humidity. And if we have a poorly sealed wall that also might have some poor insulation, it invites the opportunity for condensation somewhere inside of that wall for condensation to build. And when we add that with stick-built homes, we can get wood rot. So air tightness has a lot to do with that too, with the durability of the house. So when we first start thinking about air tightness of a home or a building, we have to identify this thing called the air barrier or the pressure boundary. Those are two interchangeable terms, but that's ideally the spot that it defines inside from outside, that one part of the house. And ideally, if you were to draw this out on a floor plan, whether if it's the floor plan or a sectional drawing, it should be continuous. You should be able to put a pencil down and draw all the way around without lifting it up. And as we can see here, we have lots of penetrations in this ceiling, which is typical in your traditional code-built home, where we have electrical junction boxes, we have mechanical penetrations for ductwork, we have can lights, ceiling fans, things such as that. And that's just in the ceiling. So we have to consider all of that as part of the air barrier. And that includes the entire duct system as well. Any duct leakage that we have is going to be reflected in our blower door number. And it's kind of like the human body, as I tell people, it's all connected. So an attic leak, you might feel attic air coming out of a low wall receptacle, just because when you have drywall coming up that meets the top plate, a lot of times that's not sealed. And if it's not deliberately sealed, when you're running your blower door test, you can feel this attic air come down into this wall and shoot out here, or maybe even lower, coming out from under a baseboard. So it was really John Tooley who came up with this idea of the house as a system, where the air barrier, the thermal boundary, which is our insulation, our HVAC system, our ventilation, it all has to work together to give us a high performing home. Everything has to be installed and designed and sized appropriately for everything to work. And we usually see this come together in our load calculation if it was complete gut rehab or new construction. But when we're going in just to look at air tightness, that's what our air barrier is. It's basically the weak points happen when two dissimilar materials meet. And when you have weak points where, two pieces of sheathing or two pieces of drywall might meet at a corner, if you were to walk around with a thermal camera, sometimes you can see where these weak spots happen. And this is a diagram we made when I was at Advanced Energy, just to kind of show some of the points to pay attention to. This is a checklist we would give to builders to show how the air barrier might work. So for an older home, if we're not doing a complete gut rehab, say if we're just doing ceiling and crawl space or ceiling and basement, and you're not tearing into the wall, then maybe your air barrier will be along the drywall and you have to treat that the best you can. If you are doing a complete gut rehab or new construction, we like to put the air barrier over on the sheathing. There's products out there that really help out with that now. But it kind of shows you here the different penetrations that you have to come to pay attention to, whether if it's ventilation or an outlet for a dryer or a bath fan, up around windows when they continue back to the wall system, and then how you transition from wall to a ceiling. There's some things to pay attention to there as well. And then, of course, like I mentioned earlier, all the things that are in the ceiling that are making holes in it, and coming up with a plan to address that is important. So here's some pictures from the field of things that we're talking about, these penetrations and top plates, like for plumbing, electrical. If we look around windows, basically, if you see daylight, that's a red flag that it's going to leak air. These stud packs, like you see here, it's like they kind of started caulking these stud packs and then either just ran out or gave up. You can see daylight between those two studs there. That's going to be a leaky point. I mentioned top plates earlier. This is as if you were standing in an attic looking down on top of an interior wall. This gap between the ceiling and the top plate is a pretty big area to pay attention to when we talk about reducing a blower door number for a house. If you think about how many interior walls we have, even the exterior walls on the interior side, how many of those cracks we have, that adds up to a pretty good size hole. So usually if you're running a blower door test to depressurize the house and you feel air coming out of an outlet or something like that, usually it's going to be coming from something like this. Chases are a big one too. Maybe in this house they were planning to run some ductwork through here and then just change the plan last minute. This is basically like having a window open in the worst possible place 24/7. So that's something we want to cap off and seal, so we don't have all that communication with attic air into the conditioned space. I mentioned corners of exterior walls can be weak points. This is a 2-stud corner. I don't see any air sealing here where I would usually like to see it, but on the back side of this nailer, hopefully they sealed on that too. They did get their top plate to the subfloor, which is good, because that's also another weak point that we see sometimes. And of course, around your windows on the rough opening, windows and doors, using this low expansion foam is a good product. If it's a really tight fit, we've seen people use caulk, and that's okay. And same with backer rod, you can shove that in there, and that does a good job as well. One mistake I have seen some builders do is use high expansion foam, like fire block foam, and that basically just ruins the window where you can't open it. It expands too much and jams it up. So they make this low expansion foam for this particular reason. And ductwork as well. So this is a ceiling return. So this photo is taken as if you were to stick half your head into a ceiling return, and you can see this gap between the ceiling drywall and the return box. So this is a double whammy. This is duct leakage and building envelope leakage. So if this return was pulling air from this room and up, it's also going to be pulling hot attic air in the summertime up with it as well. So that's something that we want to cut off. So we want to see caulk or mastic sealing this gap so we don't have that hot attic air coming in. Can lights are another one. We love can lights. We see them everywhere, especially houses built in the 90s and newer. But a lot of these so-called airtight assemblies aren't really always airtight. So they did a good job sealing this one to the sheetrock, but a lot of builders and insulators, what they're doing now is actually building a kind of box around this so that we completely put it inside the air barrier. That can be out of plywood, OSB, rigid foam board. Um, Several options to make that happen. So that was just kind of a brief rundown on some of the issues that we come across for air tightness inside of homes. I'm now going to move over and talk about the equipment that we use for testing. So for those of you who have never run a blower door test or are still new to it, I'm just going to cover the equipment and show how we get our reading that we want to get. So whether if it's a RetroTech system or an energy conservatory system, those are really the only two brands that we see in the US. They pretty much work the same way. The physics that make the equipment work are basically the same. You have a calibrated fan, you have an aluminum frame and canvas that sits up in the doorway, exterior doorway. You have a digital manometer. That's what we call a 2-channel manometer. That's basically 2 manometers built into one, which reads our indoor versus outdoor pressure and indoor pressure versus fan pressure. And of course, our tubing that makes all the connections for us. But yeah, the cloth and the aluminum frame is typically what we see. RetroTech also makes a hard panel option. So there's some different things you can use to fill up that doorway. And it's basically, whatever the user likes best. But the cloth and the frame are typically what we see most of the time for residential buildings. The frame just snaps together. You build this little rectangle out of it and it expands into the doorway. And then you have your crossbars that give you more stability in the door. Hang the frame from the bottom one, put your gauge on the top one. This 45-inch by 97-inch frame is typically what we see for most houses, but we also make a small window frame. So if you're testing passive houses or super tight houses and you want to include that doorway leakage, you can use a duct tester, since you don't need as much fan power for those houses, and set it up in a window. Or if you're testing larger spaces, we have an extra large frame as well. And same for both manufacturers. Both manufacturers have these similar options. So let's talk about how one of these things works. You can either pressurize or depressurize a house, and either way you choose to go, we are going to pressurize or depressurize to 50 pascals of pressure. And really what that comes out to, it's about like 20 miles an hour hitting all sides of the house. And that's just enough pressure to give us a differential so we can actually see what's going on and measure a leakage rate. So for this particular example, we're setting up to depressurize the house. So anytime you see the side of the fan that has the yellow, if it's a RetroTech, the yellow inlet here, or the nacelle is what we call the center of this by the motor. If it's energy conservatory, it'll be white. And then the sides where you actually change the whole side, the whole size, that's the inlet side of the fan. So this fan's set up to depressurize. So we are exaggerating the leaks in the house. And then we were able to calculate flow. So the way this works is, if you know the fan pressure and you know the area of the hole in the fan, you can calculate flow. The equation is done every time you do a blower door test with a digital gauge. The gauge is basically, now it's a handheld computer and it does all the math for you. So for a RetroTech system, you just match up the picture of whatever setting you have. If it's energy conservatory, you just tell it what ring you have it set on, and it does the rest of the work for you from there. So really the readings that we see are cubic feet per minute at 50 pascals, or we can also do air changes per hour at 50 pascals, or ACH 50. And for that, you just have to have the volume of the home. So if it's an existing home, you have to measure the volume. If there's some extra details to the house, like vaulted ceilings or something like that, I like to take a laser distance measurer and use that to calculate volume the best I can. So usually it's reported in CFM 50 or ACH 50. And if we take a closer look at the centerpiece, that nacelle of the fan, this is true for both manufacturers. There's these tiny holes, there's 4 of them around the center, and that's where our fan pressure is collected. And so you want to make sure that those are free and clear. We have webinars on our YouTube channel that go over that, but we're not going to really touch base on that today. But that's where your fan pressure is collected. So that yellow tube that you plug into the fan, it's a different color for energy conservatory. But we like to color code it, yellow fan to yellow port on the gauge with a yellow tube, red tube to the red canvas. Try to make it pretty simple. But that tube that's going to channel B, that's reading fan pressure, that's where it's coming from. It's right there at the center of the fan, and it's collected there. So I mentioned before that this is a 2-channel manometer. So um, channel A on our gauge is red on the top, channel B on the bottom. If you have a DG1000 from Energy Conservatory, it's just left and right. But as I mentioned before, red goes to the red canvas, yellow goes to the yellow fan. Um, and so basically the manometer on channel A is reading outside versus inside. So you have to run a line to the outside. That way, anytime you're using a manometer, it's just measuring one place with respect to another. So in order for us to measure house pressure, to know that when we get to that 50 Pascal differential, we have to reference it to something else. So that's why we have that cord going to the, or that tube going to the outside. And then same thing for fan pressure. We have a tube going to the fan where this other port is reading inside pressure. So that's how it can compare how hard that fan's running when it's at the right pressure at that 50 Pascal mark to give us our flow. And a question we get a lot of the times is, okay, well, how do I know which hole to set up to start? If it's an existing home and I'm not sure what to expect out of it, I usually start at A, and it's kind of similar for the Energy Conservatory too. They have a ring A as well. And basically, if I can get to 50 Pascals at A and get a flow, I'm good. But say I put it on ring A and I cannot get to 50 Pascals. The fan is running as hard as it can, and I can't get there. Then that's when I take this ring off, and then I go into my gauge, and I can just say, okay, well, switch me from A to open. And then as long as this matches on my gauge what I have on my fan, then I'm good to go. And then the same thing on the gauge. If I want to change my device, I can just hit change device. I'll put it on the newer 5000 fan, which is what's actually shown here in this picture, to match there. And then also for my reading, anytime I power, it just takes me back home. But I can tap on channel B here and say, okay, well, give me air changes per hour. And then I can go home, and then it allows me to input my volume if I want to as well. So if I know the house is, maybe 10,000 cubic feet, I can hit set, and then it saves it in there. And then whenever I run my blower door test, I can get my reading there. So let's say I want to go ahead and do that. So I'll say set pressure, 50 Pascals, hit set, and it'll give me my leakage. That's a really leaky house, 17 air changes per hour. This is just a simulator, so it'll spit something out different every time. But usually if we're testing the code, sometimes it'll be somewhere between maybe 3 and 5 air changes per hour is what we're going to be looking for, depending on what state you live in. If you're doing it for code, if you get one that's 17 like this, that's basically like a barn with the door open. That's a leaky house. But say I did this and say I got to 50, but it was just giving me 2 dashes here. Say it wasn't giving me a flow. That's when I know that I need to reduce my hole size. So maybe I would switch it from ring A down to something smaller, like maybe the B8 or B4. The plate that we put over ring A is called the B8 plate. So it goes from A to B, and it's a plate with 8 holes in it. So and the number is however many holes are open. So B8 is all 8 holes open. B4 is 4 holes open, and so on. And you can kind of get a feel for where you need to go based on how hard that fan's running. And the reason that is because the fan has to have a certain amount of pressure in there for it to be able to take a reading. So if that fan is barely spinning the blades, then we need to choke it down and make that fan work a little bit harder to give us the pressure we need for it to get a reading. And this thing I'm using here is called Gauge Remote. You can just download it for free off our website. The Energy Conservatory has their own version of it as well. And you can actually, manometers now have wireless ability. So you can actually run your blower door test off your laptop, and you can do the same thing with your phone too. You can mirror the gauge screen onto your phone and run it off your phone. So that's also another talk for another day, but that's possible to do with both brands. So in short, leaky larger houses are going to take a larger ring or be running open. Tighter or smaller houses are going to have a smaller range configuration, um, since it won't need quite as much. You won't be moving quite as much air, so you'll have to restrict that down to keep that fan working hard to build pressure inside the shell to give you a reading. And like I mentioned before, when we depressurize, we're exaggerating those leaks throughout the house. So this fan's set up to depressurize. So we're creating a negative 50 Pascal pressure differential inside, which means right on this outside skin of the building is going to be positive 50 where that air is coming in. And then away from the building is going to be 0 where that red tube is going to be reading to tell us that we've gotten to 50 inside. And that air is coming in from everywhere there's leaks, through the duct system, around all of our penetrations, around windows and doors, through those top plates that we talked about earlier. So we're just exaggerating all of that and are able to get a flow at that pressure. And as I mentioned before, you can pressurize or depressurize. When possible, I like to depressurize the building. That way I'm not blowing dampers open like you see here. So for bathrooms, kitchen exhaust and things such as that. There are times when I do want to pressurize and not depressurize at all. So for example, if there's a wood burning fireplace, I don't want to pull ashes into the living room or something like that. Also, if I know that there's mold growing on an exterior wall somewhere, I don't want to pull those mold spores in to where the occupant's going to breathe it in. And there is one example where we say don't run a blower test at all. And if that's when there is vermiculite insulation present in the attic. So that's the insulation that we used to use back in the day that had asbestos in it. And the brand that was most commonly used was called Zonolite. And there's actually a trust out of Charleston, South Carolina called the Zonolite Institute or something like that, where you can actually get some assistance retrofitting your attic to get that Zonolite insulation out and something nice and new like fiberglass back in. So if that's present, we say don't test, don't even pressurize because it'll still disturb it and maybe allow it to settle back into the wall somewhere. So it's best just to go ahead and leave that alone until it's completely removed. So that's testing a house. Let's talk a little bit about finding those leaks. There's some different tools that we can use with our blower door. One thing that we're using a lot now is this handheld fog machine. So this one that you see here, basically what it does is it produces some puffs of theatrical fog. So it doesn't really have an odor, it doesn't leave any residue or anything like that, but it just creates a nice smoke-like fog in the air so that you can identify wind currents. So I like to use this when I'm pressurizing the house because it's easy to see when that smoke is going, moving from inside of the building to out and disappearing. Sometimes I'll start in the middle of the house or I'll release some smoke inside of interior doorways. And if it's being pushed into a room, then it's telling me that room has some leaks, and a lot of times that smoke will just lead you to where the problem is. So that's a really handy tool to use to be able to see what's going on and where those leaks are located. And there's a larger version of this too. You can actually smoke a whole house or a whole duct system if you want to, and stand outside and see what part of the house it's coming out of. This can be a little tricky at times. I usually like to do spot check like this because sometimes just releasing a little bit and then just seeing where it goes is a really good start. But there's different ways that you can use smoke to find some issues. Zonal pressure diagnostics is something else we can use. That's basically when we get to our house to negative 50, we can use our manometer or a separate manometer to go around and find pressure differentials throughout the house. So, for example, we can see how attached an attic is to the house, whether to see if we have adequate ventilation, if it's a ventilated attic, or we can see if a encapsulated attic truly is part of the air barrier to see how sealed up it actually is. Same thing for crawl spaces and basements, separate rooms of the house to be able to identify leaks. We can do that as well. So that's essentially when you have a manometer and you go through the house, you have your blower door set to negative 50 Pascals, and you go around and you just look for pressure differentials. So you can, shut a bedroom door and toss your tube underneath the door and see if there's a pressure differential there. I mentioned in attics, you can kind of finagle it through the attic hatch door. So if it's a pull down stair, sometimes you can get it through that little opening where the rope comes through. If it's a scuttle hole, you can take some smaller copper tubing and bend it around so that you can shut that door on it and not pinch the hose. And then see how connected the house is to the main space. So if we're depressurizing to 50 pascals and we have this manometer completely detached from everything else except for just the attic space, the closer that number is to 50, the more connected it is to the outside. So if this manometer is reading 20 pascals, 25 would be halfway there connected to the outside. So that's a pretty leaky, attic if it's going to be encapsulated. But if it's vented, I would want more attic ventilation if it were my house. Ideally, if you're going to test a ventilated attic, you would want it to read 50. You would basically want it to be outside. So 20 isn't going to be quite enough. So that's one way you can tell if you have adequate ventilation in your attic space or not. And as I mentioned before, if it's encapsulated, if we have, something like spray foam or something like that on the roof deck, if we're only getting 2 or 4 pascals differential, then I would say that that's part of the definitely within the air barrier. If we got that, 20, 25 number again, yeah, there's some leaks up there we need to go find if that's supposed to be part of the air barrier. But if it's a really low number like that, like 2 or 4, then it's great. And if we have an encapsulated crawl space, we can do the same thing. If we want to make that part of our air barrier, we can get a hose down there somehow. Sometimes if it's super tight through the floor system, there's ways you can go outside and back in. That usually requires the user to be a little bit creative. But again, if we're getting, if we have a vented crawl and we're getting 20 pascals, we might want more ventilation, or we might want to encapsulate it to bring it down to closer to 0. Depending on what type of issues that crawl space is seeing. And I mentioned the copper tubing earlier. Like if you're going to go around a scuttle hole door, that's what this looks like. You can actually go to a hobby shop or someplace and actually get smaller tubing and adapters and copper tubing like this. So you can actually bend that around a door if you need to. And having that smaller tubing is nice because you can get into smaller areas so that you can see if what's going on inside of some interior walls. I like to use it to get up under baseboards when I have hardwood floors. Sometimes I can find an opening to get it up under there to see what's going on without having to be destructive to the house. And pressure pan diagnostics, I got to talk about that too. It's pretty similar to zonal pressures, but it's looking at a more concentrated area of the room or the wall. So I mentioned before, when we do depressurization to negative 50 pascals, we're creating a positive 50 on the skin of the building. And when we run around with a pressure pan, that's what we're looking for. So you can actually locate some duct leakage with this too. And this pressure pan it's a hard plastic shell with a port that you connect a hose to your gauge, and it has a rubber gasket around the edge. And so you go put this pan over different openings around the house. So if you put it over a HVAC supply and you read a pretty high number that's, getting closer to 50, then you have a pretty big hole somewhere in that duct branch. So you're just looking for spots where air is coming in as we're creating that pressure differential with the blower door. Let's see here. There's an example here. If you're looking at duct leakage with a pressure pan, say I'm reading 2 pascals on these branches, and then I come over here to these branches where I have a junction box, and I see 7.2 here and 7.2 here. That tells me that my problem is going to be probably with this box. So that's just a way that you can single some stuff out if you want to get that ductwork a little tighter. And that's with your blower door depressurizing to 50 the whole time. But we also use this along the shell too. So if we put this over a receptacle and we're reading something really high, like 35.2, that tells us that wall is connected to the outside quite a bit. And that's usually going to be, through those top plates again. Those top plates are really big leaky areas. So I actually found that in my own house here. So my wife and I moved into this about a month ago, and that's one of the first things I did was whipped out the blower door and went around with a pressure pan and found which walls need attention. So that's going to be my project coming this fall. And I like using this because it's fast. You can run around and actually see what's going on in just a matter of minutes. And of course, thermal imaging. I want to bring this up because it's just another way to make the invisible visible, especially if you're working with a homeowner or a client. That's the hardest thing about air tightness testing is that you can't see air. You can't really see what's going on. You can see these numbers and explain it the best you can, but making it visible in real time is really helpful to get your point across about why air sealing in that house is important. So the smoke is really great, but when you have extra tools like thermal imaging, all the better. When we use thermal imaging cameras with the blower door, we like to have a pretty decent delta T between inside and out. So we like to say at least a 14-degree temperature difference between inside and outside. If it's 10, sometimes you can still see some issues going on, but the bigger difference you have between inside and out, the better it's going to show up on that camera. And I learned this a few years ago when I first met a thermal imaging instructor who used to work for FLIR. His name's Jay Bowen. He's up in the Green Bay area. But he said, if you're going to do thermal imaging with a blower door, do that very first thing before you even run your test or anything, because you want to actually run your blower door. If you're testing if you're using your thermal camera from the inside of the house, so if you're just walking around and checking, depressurize the home so that you can see those air leaks getting exaggerated in the problem areas, but you're going to want to do it at a lower pressure. So starting out somewhere maybe like 5, 10, or 25 pascals, and then maybe creep up gradually because it behaves differently at different pressures. If you were to go ahead and run it at 50 pascals first thing, if it's a cold day outside and you have the heat on inside and you see this blue blur come across the wall, by that point, it's too late to narrow it down. So you may not be able to tell exactly where it's coming from. So that's why you want to start at a low pressure first to get a more detailed look at how that wall's looking. Because once you run it at 50, you can't rewind it. You'll have to come back the next day or, several hours later. So this is that first part of the test before you crank it up to 50 is where you can really get this stuff done. So you can see this leak in an entryway door here. So you can see the difference between -5 and -50. But this is more applicable to areas along a wall where you might have a plumbing penetration or something like that to really see exactly where that problem is coming from. So same with this receptacle. You can see that at -5, you can see what corner that's coming out of. And of course, at -50, it's going to be stronger because you have more air coming through at a faster rate. Knee walls. So this is a frog front room, a finished room over a garage that has attic space on the other side of this wall. So this corner is going to be typically a pretty big weak spot here. So we can see that coming in. Where porches tie in. So there's actually porch beams tying in on the other side of this wall. And that usually invites some air leakage if they're not deliberately sealed. And the same penetrations we talked about before. So that's a ceiling fan. So it's not sealed from the attic side. So we can see cold air coming in from there. And again, Jay sent me these pictures over and he's located in Wisconsin. So these are some good wintertime photos. A door that needs some weather stripping around it. And that's just at -10 pascals. So we're able to get a clear picture of what's going on there. If we were at -50, then this would just be more of a bright blur. So sometimes with those lower pressures, you can just get a more detailed photo. So we have air leakage and missing insulation going on in that one, and that's just at -15 pascals. And a plumbing penetration here where we can see that it's heating up that wall. So that's going to be a summertime photo there. And the good thing about thermal cameras is they're not nearly as expensive as they used to be. I mean, you can get one that attaches to your smartphone for I think $500 now. There's some different manufacturers out there that make them. I remember when I was in grad school, the one I had looked like a big Nintendo 64 that I'm holding in both hands, and that thing was 20 grand. And so they've definitely come a long way since we first started using these in the field. So they're just so much more affordable than they used to be. And you really, of course, the more expensive one you have, the better photos you're going to get. But for most cases, we can just use that little FLIR one or something like that just to get what we need. And one of Jay's tips for buying a thermal camera was, pay for resolution. Don't pay for bells and whistles on the camera, because that's stuff that you can just add on in software later on. So for buying a thermal camera, if you wanted to go higher end, that was his tip for that. Again, those top plate penetrations, this is a wintertime photo. You can really see that dumping in there, that cold air coming inside that interior wall. And of course, the leakage that we get around vents. So this is around a supply boot that wasn't sealed to the drywall. This is true for returns and bath fans as well. Missing insulation on the attic door. And that's what I've got. So now I am going to hand the reins over to Clint. So Clint, I think you should now have control.
Okay, let's see. Along the lines with that too, I mean, thermal imaging, especially, there we go. They've come down a lot in price, and it's probably only a matter of time before, there's an app in your phone that you can download and actually just have it in your phone. And something I tell people all the time when I'm in the field is, like, what's going to stop some guy who has a few extra bucks from buying one to check the temperature of his pizza when he gets it delivered, and then he's going to start walking around his house and realizing there's a lot of problems in his 2-year-old home,
Yep.
And speaking of problems, air leakage. So this was a picture we put together 6 or 7 years ago that before the 2006 Energy Code, there was actually, if you added up all the air leaks for the code minimum to pass and put them together, you would get a 30-inch hole. So this picture is supposed to be what a 30-inch hole looks like on a 2,000 square foot home. So homes have continued to get a little tighter, and that's something that I've noticed personally in the field too, is that we're starting to finally build a little bit better overall, but there's still lots of improvements we can make, and that's what I'm going to talk about today, is some of the low-hanging fruit that we can try to get with air sealing. But Sam, I think in the new manometers, you can actually punch in the equivalent leakage area, right? And have it tell you this house has a 26-inch hole or something.
Yeah, that's another output feature that you can choose. So you can say, hey, I want to see the equivalent leakage area in this house, and sorry, I got a call there. Yeah, so you can actually spit that out on the gauge itself. So you can have it say, like, yeah, there's 30 square inches, and you can just have that pop up right on your manometer so that you don't have to do any extra math. And what I used to do when I was with the homeowners, actually do that and then draw it out on the floor and say, this is what we're looking for. I'll add it up somewhere all throughout this house. So.
Yeah, and it adds up really quickly. I mean, you see this, this hole is bigger than probably any of those windows, and it's open year round all the time. You don't necessarily know where that air is coming from. If it's coming from the attic, it's really hot and coming into our conditioned space, or our conditioned air is then leaving the attic and we're not controlling it. So it's really important to understand. One of the things that we know about it, the importance of air sealing, is with convection and air movement through insulation. So we have a penetration here in the wall, and that air then moves through the wall cavity and into the home. If we put any insulation into the wall, no matter the density, we're going to stop the convective looping. But that doesn't stop air from moving through it. So we might slow the flow of air with fiberglass or cellulose or even open cell foam, whatever it might be, but we're not necessarily going to stop it. And as the Thermometric project pointed out a few years ago from Building Science Corporation, that our value is our value across the board. There's not any one thing that performs better than others, but the real determining factor for performance is air moving through it. So if we can stop the air from moving through it, then our R13 or R23, whatever's in our wall, will actually perform much closer to that rated R value. But we know that. The other thing we know, and you mentioned it earlier, is there's three forms of water. There's solid, liquid, and then vapor or gas. And water vapor travels on air. So if we have air leaks, then we will then have more water in our walls and building. And this is another study from the Building Science Corporation that shows, they had a 4x8 sheet of gypsum, and they ran it through a cycle, and they got 1/3 of 1 quart of water. They did the same test, but they introduced a 1-inch square hole, and they got 30 quarts of water through it then, because all that water vapor is moving on the air. So the idea that our houses need to breathe is what was making them wet in the first place a lot of times.
It's pretty amazing when you look at these numbers too. These are pretty conservative. So I think this is over a week's time in the heating season. And I know I see that 40 relative humidity, 40%. That's low. That's low compared to, like, here. It's hard to keep my house below 60.
Right.
And that's because a lot of it's because of air leakage, but that it gets way worse than that in a lot of houses, depending on where you are in the country.
Yeah. And like you said, 40 is pretty safe, but I'm not in the South, but here in the Midwest in the summer, yesterday we were sitting around 80% humidity. That's pretty high. So we had a lot more water vapor in the air, so we had a lot more water that could leak into our walls that way.
And just having that 1 square inch hole makes that big of a difference.
Huge difference. But remember, we had a 30-inch square hole prior to 2006. So that's a lot of water coming into our houses. But some things that we don't think about when in terms of air sealing is noise. So this is pulled from one of our data sheets, one of our BAT data sheets, and it was third-party testing, and it's just showing the STC ratings of a couple of different assemblies and how adding insulation helps. But STC sound transmission class is only looking at the structure of the assembly and how it's blocking noise. So when we just look at this first line, single stud, single layer gypsum with insulation, we have an STC of 38. Without insulation, we have an STC of 35. The way that people perceive these STC points, 3 STC points is just noticeable. 5, there's a clear difference that we can hear. And then 10 STC points is about twice or half as loud. But the interesting thing about this, and something that we don't think about with air sealing, is that when they are doing these tests in acoustic labs, they're going to use whatever insulation's available and cheap, because thickness actually matters more than density. But they're testing the structure itself, and so they need to remove the variables. And one of those variables, of course, is flanking paths. So they're going to use some sort. They have like because I've been able to see some of these, they have like an acoustic putty. It's like they're playing with Play-Doh. They roll it out and they stick it around the wall because they need to air seal it to remove the variable of the flanking path. So if we actually look at a STC test with a sealed wall versus an unsealed wall, we see the bottom one here, STC of 37. That's really close to the 38 we were just looking at. But without any air sealant on the wall, we have an STC of 27. So, if we go to USG and pick out something from SA200, an acoustic assembly that has a STC value of 63, and we spec it on a building and it gets installed and put in, but then it doesn't get air sealed because it doesn't really mention it in the spec, then we're only going to have an STC of 53. We're leaving those 10 points on the table, which in multifamily buildings can be really important, or if you're close to an interstate or some other big noise producer. This is a big difference in terms of just a little bit of air sealing can make a big difference in STC value.
I would imagine this would be very valuable in urban areas, for sure.
Yeah, absolutely. And it's kind of amazing too when you talk to a lot of people that design buildings and things, that they don't, they don't know this. They know how, steel studs affect a wall, or they know how resilient channel affects a wall, or maybe we'll put 2 layers of drywall on this side. But this is something that's, can be done pretty easily, and is actually done in the test that gets left off the table in the field. And the other one that's really come to play in the last couple of years, and you mentioned it earlier too, is indoor air quality. If we have an air leakage pathway, then we clearly have a contaminant pathway. And this is a great picture we got from a retrofit a couple of years ago. People in the building performance world have probably all seen a bath that looks like that in an attic. It's just a clear outline of the top plate and the wire penetration, where, because of pressure differences, air is moving through the bat, and then dirt and dust and all sorts of other debris is getting caught in the bat like a filter. And so what we did, of course, is we sealed up the top plate in the third picture. But one thing that people don't are only starting to think about is how what's around them gets into their house. And so there's been a handful of studies recently that show living next to an interstate within like 3/4 of a mile, you don't get just carbon monoxide, which is what people always thought, but you're starting to see with more studies, you're getting diesel soot, atomized tire particles, road particles in your house that you're breathing in. So air sealing your house can cut these off. And it's different for everyone. So if you live next to a field, then maybe you're getting dirt when the farmer comes out to disc, or herbicides and things like that might be coming in your house. Or if you live next to a metal foundry, what's getting in your house then. We know it probably from living in at least me living in apartments in college. I knew when my neighbors were having dinner because I could smell what they were making. And that's just, hopefully it was good smells. If not, then I would consider it indoor air pollution. But it's just coming through walls and different leakage pathways into my apartment, and I can then smell it. So this is really important too. And our friend Joe Medosh works with Hayward Score, and anyone can go on their website and actually take a evaluation of their own home, fill out a questionnaire, and see how they are doing with indoor air quality.
Yeah, the research that they're doing at Hayward is pretty awesome. They're looking at stuff that no one's really looked at before. They're actually taking, some building materials and breaking it down, to the ingredients that go into it to see what actually off gases. And so no one's really done that. And that's just one example. So it's definitely, if you've never been and if you care about indoor air quality and that's something you want to kind of focus on your business, Hayward Score is definitely something to keep in mind to check out.
Absolutely. And it's we can go down an entire rabbit hole with this, but it's amazing to think I'm sure you've seen Joe's presentations on this, but Bill Hayward, who came up with the Hayward Score, built a new home and had like all green, low VOC products put into it, and then closed the house up when it was done for 2 days. And I forget the levels, but the CDC level, for VOC content is at the bottom of this graph. And after 2 days of having the house closed, they had to like extend the graph so much because there's so much stuff off gassing, and they use the good materials.
Yeah.
So anyway,
again, it's that whole house as a system approach. When you
Absolutely.
Close the house up and you don't have filtration and ventilation mixing out.
Yeah. And then they have,
work.
The graphs that show introducing ventilation, and of course the VOC content just drops overnight, but it's all important.
Absolutely.
If I get my slides to move on here.
There we go.
Here we go.
I wanted to give one more example too, just while we were on indoor air quality. We have, there's one town here in Eastern North Carolina where I'm friends with the building performance guys, and they had a lady that has terrible asthma, and she knew she had mold in her crawl space, and she couldn't quite afford a crawl space retrofit. So her duct leakage was really high. So all they did was just seal her duct leakage in the crawl space, and her asthma symptoms were cut in half almost immediately.
Yeah,
So yeah, indoor air quality and air tightness definitely go hand in hand.
absolutely. I mean, we keep going deeper here, but Kevin Kennedy, another Habitat Xer with Mercy Children's Hospital in Kansas City, is uh, now getting, he's got families that were coming in 3 or 4 times a year and having hospital visits with their kids. And he's having insurance companies pay for retrofits on those homes because, they pay $4,000 for a retrofit and suddenly they have to stop. They're not paying $15,000 a year in hospital visits
Wow.
because of indoor air quality. I mean, it's really amazing what we found out in the last 4 or 5 years with this. But anyway, in the last couple of years, I would always go out and work with installation and air sealing crews and think that like we were making the big difference here in homes. But in the last year or two, I've really come to think that the builder makes the biggest difference, and we can get a house to 3 air changes per hour relatively easily just with hammer and nails and paying attention. So this is a screenshot from a video that we put out recently. Thanks for all the plugs, by the way, Sam.
Sure.
But I'm talking about air leakage, and just a common thing that I see is, air leakage in gable walls, and just by the way they're built. And one of the things that I'll say now and keep saying is we don't want to abandon common sense. If we can see daylight, or in this case, if I can stick my hand through a hole, it's pretty big and we need to seal it up. So in this instance, a gable wall, the way that they're built, they have in every single wall cavity, they're open to the attic where my hand is sticking through. Above this plate would be attic, 120-degree air, free to move into 70-degree conditioned air. And on a 2x4 gable at 16 on center, in every stud cavity, there's about a 50-inch square hole. That adds up really quick. If it's a 2x6, it's close to 80 inches. And so, it can be easily overcome with some scrap pieces of OSB or 2x4s in there, insulation board or foam board, something. And ideally it's air sealed, but even if it's not, then we're cutting down that gigantic hole to make it only, half an inch or 1 inch or something like that instead of 50.
That's where it's fun to use that EQLA function on your manometer if you're doing the blower door test and just watch it drop. Go plug up a few of those and then run the test again, and you just see that lower number, and it's like, wow, it did something.
Yeah, we did a training last year with HPIP, and we were actually able to do, because usually we're on new construction sites, so we set up like the blower door tent and go through it, but you can't actually do the test. But we were able to get on an existing house and blower door test, and we actually found a couple of leaks and sealed them up in the basement rim joist area. And so we had, I forget what the CFM was, but we dropped it by about 70 in just about 3 minutes of work.
Wow.
And it was really cool to have, students there and show them like, here's the instant difference that we made on the manometer in no time at all, but we'll move on to the next one. So again, we can't abandon common sense. I mean, a lot of times, there's not going to be a lot of leakage that comes through this joint, the bottom plate to the subfloor. It of course can leak. We see it here. There's a lot of daylight, and when we zoom in a little bit, I am actually sticking my finger in. I am not all the way in the corner. I'm actually only about a quarter of the way down. So in the corner there on the left, I could about stick my whole hand under the plate.
Wow.
And that, I don't know if it was warped materials or what happened exactly, but there's a big hole right there that needs to be sealed that easily could have been avoided with, in the construction phase.
Yeah, going back to the responsibility on the builder, that's something that I've seen in the field with new construction too, is that sometimes materials are just stored outside on site for, several weeks and get rained on. Yeah. And then they get installed and then they dry out and they warp. Like we've seen that a lot.
Yeah, or even, you can get new material on it, over time sitting on a site and not in a pile, it starts to dry out and shrinks, and you get an extra hole, which we can't control a lot of that, or some of that, but most of the things here we can control. And I am not wanting to step on any builder's toes, but hopefully open some eyes that there's a lot of little things we can do better with minimal investment and have a big return on air sealing. Um, Rims and bands are one of these, and I think this is another video we put out, is just going over the way they're usually framed. Is, you have an 8-foot wall, so you use an 8-foot sheet of OSB, but below that you have a 1-foot band joist. And so what do? You find some OSB and you rip it down, or maybe you have scrap material or something that gets put to cover the band. And so because of that, it's usually leakier. So why not use on your 8-foot wall a 9-foot sheet of OSB and just cover it all in one piece? There are now systems that are becoming more and more popular that do all the air sealing from the outside on our walls, which is great, and it works well. But one thing that I still see a lot in the field, even with those, is on the rim joist in particular in basements and crawl spaces, the bottom of it is not sealed to the foundation. So if we have, like in this instance, there's a daylight pouring in from the bottom of this rim, usually what I see is that doesn't get sealed. And it's not something that our air sealing crews do a lot, is focusing on the rim joist either. So, this house probably stayed this way. And then, hopefully we'll get into some examples of things done well here, but this is me looking from inside, looking out towards the garage. There's a second floor above us, and the builder put in this band between the floors. He put lumber in between it. So, we're ideally going to air seal this and make sure it's closed. The garage is separate from the house this way. But even if we didn't, we now no longer have these giant holes in every single cavity because they're closed off. We've, drilled through to have the sprinkler fire suppression run through. There's a wire penetration, but we went from having big holes now in this one spot to much smaller holes that need sealed. And you've talked about it earlier, chases. This is a fireplace on an interior corner. And the builder did their due diligence. They have OSB capping the chase, and then where the flue pipe meets the OSB, they've got space around it, and they have space going up built into the pipe so we can put insulation directly on it. But if this wasn't capped off like this, whose responsibility is it to cap it? And do we just leave this 6 square feet open to the attic and have attic air pouring in or house air running out? This is a huge hole that was sealed up because the builder did it. And then in retrofits, drop soffits and tray ceilings and things are always a big leakage issue, in energy penalty. But here the builder actually framed the top and the back side of this in with OSB, so it's got an air barrier on the top and back side of it. What would be even better is if they used some drywall and ran it out a couple of inches on the top and bottom, and then when the drywallers come, they just run their board right up to it and tape it, and then it's sealed all the way around completely. This is a big one, because a lot of sites that I visit, when we have a tub or shower or fireplace or staircase on an exterior wall, a lot of times it's already installed by the time we're there to do insulation or air sealing, and there's no air barrier, and we don't know if there's, it's really hard to get insulation back behind it and try to do it well. So whose responsibility is this? Is it the builder or framer? Is the plumber putting their own air barrier and insulation in, or have we scheduled the insulating crew to come out, one extra half day and do this stuff? The easiest solution is to plan ahead and not have these things on exterior walls. If we put them on interior walls, then we eliminate the problem completely. But this is a good example of insulation's back behind there, and then they have OSB over it, so they have an air barrier going over it as well. Here's one for you. This is a bonus room, and the knee wall was actually backed when we were there to do work, so you had something to actually air seal against, and then when you put in your insulation, we have an air barrier on the backside to try to keep that really hot attic air out of the insulation and moving through it. But then one extra thing that the builder did was he cut pieces of foam board and stuck in the floor joists of this bonus room. So he insulated underneath of it or we insulated underneath of it, and then he had these joists capped off to try to keep the attic air from moving under the bonus room. And again, we didn't air seal it because that wasn't in the scope of work that the crew was supposed to do, but you went from having a giant hole in each one of these floor cavities to a much smaller hole because we have a rigid material in there.
It's rare when you go into a house that has a frog like that's comfortable. Like that's
very rare.
I'm in one right now, and it's this summer, and there's usually been a 5-degree difference, and it's just gonna get wider as we get into warmer weather here. But I know I have my work cut out for me up here. I have to cut out 2 attic accesses because there's no way to get to the adjacent attic access there. So the planning on this house just wasn't there.
Yeah, and just one pet peeve of mine is a knee wall is open to the attic. So it should get attic insulation values, but it's technically a wall, so we also just put wall R value in it. So this knee wall, I can't remember what it had, but it probably had R13, and why not? Like the code here is 38, so it should have 38 technically, but I don't know. Yeah. It's a pet peeve that is often overlooked in homes, but at least they had backing and they had blocking, so steps in the right direction here.
Yeah, and then I guess people forget that's an exterior wall. The attic is outside, and another thing that backing does, other than provide an air barrier, is it keeps that insulation from falling out. There's been countless attics I've gone into on knee walls where it's just doubled over and fallen out.
Yeah,
so it keeps that from happening.
Yeah, they put it in, and at the very least you could use some sort of strapping, but that's just not common practice. That's an extra step, and no one does it. So
right,
it's always in retrofits. You're right. It's always a huge issue, and John Tooley made a name for himself by retrofitting bonus rooms.
Yep.
Because he saw the opportunity. So. This is an example of, I think maybe this was a change order or something in a house, but they had a tray ceiling in a bedroom and capped off that soffit. But then the electrician came and put in some can lights later and just cut giant holes through the top of that. So it's no longer blocked off. We have these giant openings into the tray ceiling. So it was a good idea, and then later just butchered. So we need to pay attention to what the crews are actually doing on the site when they're there working, and make sure that all the products get installed correctly. My first piece of advice is maybe don't let Nick and Steve on your job site to do the house wrap, but there's not any one magic bullet of a product. Everyone has certain applications where it might shine. But every product should work if it's installed correctly. And one of the builder's responsibilities, or the general contractor or whoever, needs to be making sure that things are done correctly. This instance here, the Tyvek, it's okay overall, but now we have, I don't know, a couple hundred extra holes.
Yeah.
As John Straub says, a staple generally leaves about 2 holes. One for each end, so lots of extra holes here just because some guys were being funny. So it is a great picture. You use it in a lot of presentations.
Absolutely.
And then this is another pet peeve. So we have to get past things like this. I mean, one, we shouldn't be using pan joist returns. Sorry if you hear my dog barking.
That's okay.
We shouldn't be using pan joist returns, but at the very least, we definitely shouldn't be putting them in attached garage walls. So anytime this air handler kicks on, it's going to pull air from the return grill, but it's also going to pull air from wherever it can get it. And air is it's going to take the path of least resistance. So in this particular example here, we don't have a bottom plate that spans the cavity where the joist return is. So when the drywaller comes and they hang their sheetrock on the back side here, we're going to have still a gap right here, which is going to be pretty substantial. So we're going to pull a lot of air from the garage. And it's not just that we're going to pull air from the garage, it's that we're going to then distribute it through the entire house through the air handling system. So there's going to be exhaust fumes, there's going to be gas, there's going to be other things that we're storing out there. I always give the example of, what if these guys, the family that lives in this house, they make really intricate models, or they build furniture, and so now there's paint and lacquer and all sorts of things off gassing and moving through the house just because of this.
So, yeah, you think about what you store in your garage. You store everything in there you don't want to store inside.
Right.
Yeah. When you do something like this, you're bringing it in anyway. So
yeah, anything I don't want in my house goes into the garage.
Yeah.
And when you have a pan joist return like this, it just takes it through the entire house then. So then where are we actually going to seal if we have all the, it's not an exhaustive list of pictures, but if we have all that taken care of, then where can we focus and try to make a difference? We need to know that so we don't do things like this. This is the code inspector in this area, or maybe the builder, I can't remember which, but kind of mandated that the air sealing crew seal these blocks. And this is a partition wall between units, and you can see the bottom, where the drywall would meet the plate, and the slab here is just completely open. It's not sealed at all. So really where we should have been focusing is around the outside of this wall, maybe the top of it, and not so much right here, but this passed inspection. So we definitely want to do better than this. So I don't know who said this or came up with it, but we want to always take care of the big holes first. Again, we can't abandon common sense. So if we see daylight, or if I can stick a finger or a hand in it, we want to seal that up because there's, of course, going to be more air leakage through it. And then we're going to try to seal high and then low in the building and then out. And the reason for that is we want to try to take care of stack effect and natural pressure drive in the building, which is going to help induce more air leakage. If we seal high and we seal low, then we've taken care of where the pressure and air leaks in and out of a building in most cases, and then we can focus then on moving out into the walls. So what do I mean by big holes? Go ahead.
Oh, sorry. I guess one thing that a lot of people don't realize, especially homeowners, is that you can have air moving through walls and through insulation without any wind blowing outside and without any fans running inside. So there's this whole stack effect thing that still happens. So
Absolutely.
you can just air sealing will stop that altogether. And
that is the reason why revolving doors were invented. Is because as we started to build higher and higher, we were building essentially a bigger and bigger chimney, and all of our air in the building was exfiltrating out through the top, and all the air was infiltrating through the bottom, and you couldn't pull open a door at the bottom of these high rises because there was so much pressure on it. So then you had a revolving door. It was never open, it was never closed. It's also another fun fact for you, Sam, why if you ever see like a crawdad mound, they build mud up. They're building chimneys so they get airflow through their holes.
Huh.
So now you know.
Yeah.
Remember that in trivia.
Yeah, that's a great example.
But these are a lot of big holes in this building. I make the joke that before he was a famous wrestler, Hulk Hogan was actually working on a retrofit crew, just punching holes in walls to stick an insulation hose in. So this was a remodel we were doing, and we had no intention of doing any sort of energy work really, other than, uh, replacing the insulation in the attic and in the rooms we did work in. But this, we opened the walls up and then we saw this and thought, well, we can't just leave this. But every one of these holes was around 28 inches square inches of leakage. So that adds up a lot. Huge areas. So we had to seal these up before we did anything else. Otherwise, what's the point of putting insulation or anything back into the wall cavity?
Sure.
So we're going to seal high. So you mentioned earlier, we're going to focus on sealing penetrations through drywall. So top plate to drywall, HVAC terminations, electrical penetrations, and chases. First, always focus on top plates because that adds up very quickly. In my house here, it's not very big. I have, I think, around 340 lineal feet of top plate. And if I have just enough space between the drywall and the top plate where I could stick a quarter into it, that adds up to, I think I had like 21 inches or something when I did the math. And of course, there's always a big pressure difference and a big delta T between the house and the attic. So this is where a lot of leakage can happen. So we want to seal off the top plates and all the penetrations through the plates, like this wire penetration here, and just knock that out right away. And we can do that in any home, no matter what the builder has done anyway. And one of the ways, easiest ways to do that, if I advance, there we go, is with a gasket product. So we make one. Of course, there are a litany of others out there. The only thing I would caution is you want to make sure that the builder and or drywall contractors are on board with it. I know you and I have talked that we've been in homes where we've gone in the attic and there's a big pile of seal on the drywall. And so what they do is they hang the first sheet and they go around and peel off all of the top plate gasket and throw it up into the attic and keep moving because they don't want to deal with it.
Yeah.
So
or they'll slide that drywall up the wall and just bump it up into the attic
just
that
wreck
way.
It. Yeah. And there's a lot of products that adhere to the top plate well. We make one. There's an Owens Corning product. There's Dow. There's lots of others. But the important thing is to make sure that we know it's going to actually be there to do the air seal. And I know I've been on a couple of sites where I've talked to the drywallers where they're using like seal type gaskets stapled to the top plate, and they're moving their board around it. And I asked, like, is that really inconvenient? And the answer I've gotten the handful of times I've asked is, it took 4 or 5 sheets to get used to it, and it's not a big deal. But that involves talking to another contractor and making sure they're on board with the work that's getting done. HVAC penetrations. I should go back real quick. I actually have some numbers to share that top plate leakage. We've been on retrofits. I'm sure you have too, where you get like a 50% reduction in leakage from just sealing the top plate. But on average, in a lot of new homes, and every house is different because they all have different amounts of plates, but it's about somewhere between 0.5 to 0.7 cubic feet per minute per lineal foot of leakage with top plate. And the visual I always have is a cubic foot is roughly the size of a basketball. So that's 1/2 to 3/4 of a basketball for every lineal feet of top plate of leakage.
Wow.
With a duct boots and HVAC penetrations, this was pretty clear to see there's going to be leakage here at this bath fan. The drywallers cut a much bigger hole there than what's needed. This averages around 7.5 cubic feet per minute per boot. So you think you've got 6 rooms. So if you have a good HVAC system, you have at least 6 returns plus a couple of bath fans and then maybe one bigger return. So that adds up, really quickly. when you have 7.5 basketballs leaking out of every single one of these at 50 pascals. Can lights, like you said earlier, we love can lights. This was actually taken from my house. The drywallers did a great job, but there's still this blue stuff here is actually, sealant that I put in around the can lights to try to seal them up. And because they're airtight can lights doesn't necessarily mean they're airtight, because they are still allowed to leak 2 cubic feet per minute at 75 pascals. So we want to seal those up. They do come with gaskets. Hopefully the electrician or whoever's putting these in puts the gasket on the can light. So when it's stuck to the drywall, it actually gaskets itself off. But then there's also, older can lights that aren't insulation contact rated. We see this clear outline in the old insulation where there used to be some sort of cover or bucket or something. But we don't want to just set it up there. We actually want to seal it to the drywall itself, so we have an airtight can, because we've got these big holes here on the back, plus the hole that's cut around the drywall, plus the hole through the housing and everything. So that can add up really quickly. Those are actually average around in new construction still 9 cubic feet per minute per light under 50 pascals.
Yeah, that adds up. I mean, you can have some houses that have 50 of those things, and yeah, that adds up to be a big hole for sure.
I was actually in a home improvement store here when I was working on my house, and a guy asked me for help. He was looking for a certain type of light and thought I worked there. I helped him anyway, so maybe I should get a job. But I found them for him, and then he wanted like 78.
Wow.
And I said, if you don't mind my asking, what do you need 78 of these for? And he said, I'm tired. They were LEDs. And he said, I'm tired of replacing the light bulbs in my can lights. And I said, you have 78 can lights? Like, if you're willing to drop $800 on light bulbs, can I interest you in a retrofit?
Yeah.
But I had my own problems here at my house, so I didn't Anyway, talk about adding up. 78 can lights at 9 cubic feet a minute that's a lot.
Yeah, that's huge.
Yeah. So we're going to seal low now. So we're going to focus on rim and band joists and foundation walls, and then low exterior penetrations. And this is a wall from an addition. So we have it's a walkout basement here. We've got the concrete block wall, but then we actually have a few different types of lumber here and wall transitions. So we've got the band joist up here. We actually had foam board here. It was I think a 9-foot wall and an 8-foot piece of OSB over here for racking. And so there's a lot to seal here. Especially, we want to focus on these seams that are just open to the outside when we're looking at it. But then again, a lot of times in these things you can see daylight. Foundation walls, poured concrete walls typically are flat mostly, but there's sometimes, I don't have a picture yet, but sometimes you'll see there'll be a dip, where maybe they got a tool in or part of the form was there. So there's going to be a big gap under the sill plate that we can seal up. But in general, band or rim joists leak about 1 cubic foot per minute per lineal foot, or around half an air change per hour when you add it all together. Transitions between walls. So we have again, here's a basement wall into what would be a regular exterior wall for walkout. There's ways to fasten this, but maybe they adhered to it and it's just not fastened well, or it wasn't tight, or maybe the OSB dried out overnight or something. And we have a lot of daylight right here. That adds up. Clearly, when there's daylight, we need to seal that. And then, here we go. So basement into a crawl space, looking towards the crawl space. We've got our sill plate and then our sill seal gasket, but our gasket can't actually do anything right here where we have this big joint. So even though we have an air sealant here around the plate and framing, there's still places where we need to pay attention and try to seal that up And it's not only helping with the air seal, in this case in particular, it's going to help probably with pests getting into the basement and into the house. Seal out. So this is where we start to not pay as much of attention. The fruit in the tree gets a little higher to get to, but I do have asterisks here for garage house common walls and partition walls, because those tend to be leakier, just by the way they're put in and built. And they're all, of course, they matter with indoor air quality and fire safety, which we'll get into here in a second. But there's also panel joints, paneled wall sections. Here's one. We can't ignore this because there's a lot of daylight coming through here. Sill seal for reference. And then exterior penetrations, we don't want to leave those unsealed. And then last is sheathing joints unless we see daylight coming through them. So here's a garage wall looking out, and the reason why this is an issue is because when we are there to do any sort of air sealing work, more often than not, it's not backed. So we don't have anything to actually go out there and do air sealing to. So if it gets left unsealed, we do have a little bead of sealant here on the bottom plate to the subfloor, but beyond that, there's not a lot to do. So if it gets left unsealed, they put drywall on both sides. Drywall actually kind of puckers around the screw a little bit, and we have induced leakage then around all those fasteners. So garage walls actually amount to around 1/4 of an air change per hour. And for no more of the space than they take up in a house, that's a pretty substantial gap. So one thing we can do, the builder or whoever can get on board, we can actually have drywall put on one side, so then we can seal it to the plates and everything. We can seal this, electrical penetrations up and try to cut that leakage off. Or again, we can try to use a gasket type product on the exterior of the wall itself, and so when the drywall then goes against it, it's sealed off from the house. Partition walls in multifamily buildings is another big leakage point, because as you can see in this picture, there's a lot of things to seal. There's a lot of places where air can leak through, where the material is broken and met with something else and starts on the other side of it. The actual scope of work for one of the more popular spec walls in multifamily is a really long list. Again, this has to do with acoustics, this has to do with indoor air quality, and this has to do with fire suppression and fire safety between these units. And it's really important that when you have a wall that's put into a building, it has a certain spec or certain fire rating, that we then use air sealants to seal the wall off to help stop draft and everything for fires, but we can't have it interfere with the fire rating itself. So if we have a 2-hour rated assembly and then we fill it with something that has a flash point of 100 degrees, that's not going to help the rating of the assembly at all. So we have to, do due diligence and make sure we're not hampering the fire rating and life safety of these walls in multifamily buildings. Then we have penetrations, another area to focus on as we're sealing out. So, we've done the air sealing work around the outside of this, but what we missed was these where the wires actually go into the box. These two giant holes here, and these two, they're not punched out, so they're not quite as leaky, but there's still holes on the back. We could. I've been in homes with where builders are actually coming back and having someone on the framing crew or someone, if they have a lot of these penetrations, they'll come back and hit it with a froth pack even. And so, one froth pack per house or whatever, they'll take care of the 20 penetrations and seal it up completely. Or we could use airtight boxes. There's a lot of different ways to seal these up, but, and then the last point here would be sheathing joints. I see this a lot in the field. The only place we focus our air sealing efforts is sheathing joints on exterior walls. But as we've just been through, there's a lot more places where we can make a bigger return on our air sealing investment. There are, of course, places, if we're using materials that aren't as rigid, we might see more daylight, or maybe in this case, we did seal it, but then it broke away. I don't know if the sheathing on the outside got bumped into or something and broke this joint, but if we see daylight, we still do want to seal it. If we are trying to get really tight, we want to seal it up too. Or if, on the outside, if they're using something like a zip tape or doing all the air sealing work from the inside, then we don't need to focus our efforts here at all. We can do top plates and other things and try to make a bigger difference. And I think that might be, oh no, one more, sorry. Again, like I mentioned earlier with the builder due diligence, we want to use the right product and then use it correctly. So this was a house I was in over here on the left, where all these exterior penetrations, they actually had the electrical box sitting on the outside, which should be more airtight, but they were sealed with duct tape, and it's not even the good duct tape. This was the cheap stuff. So
Oh man.
When the sun hits this and they have solar vapor drive, this is just going to peel right off the back of the wall and not have any sort of air seal if there is one already. And then again, there's a lot of products that work well and can work well if they're installed correctly. A lot of products require tooling, and I rarely ever see them tooled. So when I do, I always get a picture. It doesn't do us any good to air seal if we don't use the product correctly and actually air seal it. And this one on the right passed inspection. So that's kind of what we're up against sometimes. So, and then I think that's all I have now. So.
Cool, Clint. Well, thanks for that. As you see on the slide, we RetroTech has a YouTube channel. If you go to YouTube and to search RetroTech Energy, we have basically anything you want to see about air tightness testing is on there. And same for Knauf. They also have an array of videos that go over some of the proper installation of insulating and air sealing products, some building science best practices as well. So check out their content as well. The stuff they've been putting out here this year and last year has been really great. It's really clear and easy to understand. But that'll do us for this session. Thank you for attending. And if you have any questions for us, feel free to reach out. Thank you.